Remember, we are still talking about electrodynamics in action and following our syllabus which we had already. We are now in a chapter which is called optics. And I would like to start with a quotation which comes from the work of the certain gentleman named Robert de Grosseteste, who was probably the first scientist, modern scientist of our era. He lives in England. He was a bishop of, one of the bishops of the, at that time still a Catholic England, and he was also for a while president of the Oxford University, involved in this famous case of the university being closed by the kings and so forth. And he was a scientist who had been the first one who, at least in the written materials, underline that it is the experiment which has a final saying in science. Then unless we can do the experiments and then whatever we say is just mere talking, not really something which is worthwhile. His student was Roger Bacon, and they both laid the foundation for the chapter of science which is called optics. And sure enough, the optics comes out from our attempts to understand why do we see something and how do we see something. So we start with the history, and that is probably the first magnifying glass which has been ever found on the Earth. This is so-called Nimrod lens. It was founded in the 19th century by one of those British explorers who were exploring various places. It was found in the ruins or remnants discovered in, I believe it was 1860 something. In Nimrod, Nimrod is a town in Iraq. It's a suburb today of Mosul. And that is a device which is a lens with the focal distance 12 centimeters. It's about a 3-4 times magnifying glass, and it's not clear actually for what it was used. Whether this was, there are various theories. I mean, it was found in the rubbles, and one of the explanation is that it was used by the craftsmen to produce a very fine little signs on the jewelry or whatever they have been making. The other is that it was used for some astronomical observations, but most probably this was actually used by the craftsmen for jewelry making, because it was found in what they think was a remnant of a shop, of some shop where things have been made. So the attempt to understand the optical phenomena, and actually a concept which you might remember from the high school, that there is a light ray, right? In the high school, the light is always drawn with a ruler, and you draw the line, and you have a rays only. It's not clear of rays of what are those lines, and anyway. But this very concept came from Euclid, and then in the 200 of our already in our era, Ptolemy, the same fellow from astronomy, he wrote a book which was called Optics, where you can find already certain formulas which we are now teaching our children in the schools, like, for example, what is the relation between the distance of the object and the picture and a focal length of the lenses. And then nothing really important was happening in the optics, and we have the 13th century, the beginning of the 10th century, and the optics becomes extremely I mean, there are lots of people, there are lots of activities about the optics. One is, of course, this Robert Grosseteste, about whom I was just talking, Roger Bacon, famous Roger Bacon. In our part of the world, it was Vitello of Silesia who wrote one of the very first textbooks of the optics. And then again, nothing was happening. Slowly people learned how to make the magnifying glasses. The glasses were invented. We will be talking in a second about it. And the major breakthrough was in the 17th century, when following discovery of a Dutch craftsman who managed to already produce a very high quality lenses. The quality of those lenses was not that much different from the quality of the lenses which we can buy today in the shop. Maybe not the quality of the lenses used in the Hubble telescope, but the good quality. And then Kepler had written a book about the foundation of the optics. This is a very interesting, because Kepler had also written a lot, as you know, about astronomy. The question is that Kepler was very short-sighted. He had very bad eyes. He had never made any observation by himself. It's not clear how he discovered this hexagonal shape of the snowflakes, but all his astronomical observations are actually observation by his predecessor as an imperial astrologist, by a certain gentleman named Tycho de Brahe. We will be talking about him in a moment. Then, of course, it was a discovery of the fundamental laws of the reflection and transmission by Snellius, and it was René Descartes, Cartesius, who was trying to develop a theory of light. What actually is the light? And the beginning was, of course, and that was the beginning of a discussion whether lights are waves or particles. And Robert Hooke, who was a competitor, he was in a competition with Newton. He actually was for the wave theory of light, and we will see in a moment his apparatus. But there was also Isaac Newton, who is much more well known, but the history plays the tricks. Robert Hooke was also the man who actually first proposed the laws of gravity. Robert Hooke was an interesting character. He was a friend of a king. They used to go to the bars together and drink and do various strange things. But he was a poor man. He was not independently wealthy, and therefore he had to work to live. And that is why he was less, he published less in the contemporary language. His Higgs index was not so much. No, not the Higgs. What was the name of this crazy index? Well, anyway, one of these publication indices was, in our modern language, was not so good as Newton, but anyway, we still remember Robert Hooke because we have a Hooke law, And we also, when we drive the car, we drive the device which in each in gearbox has this device which has been invented by the Robert Hooke. All right. And of course, the optics was stimulated by astronomy. And already in the 18th century, a Scottish astronomer, James Short, manufactured a telescope which had the length of almost 40 centimeters. And it was at that time the most powerful telescope. And actually a precise measurements, astronomical measurements, started not so much with the Galileo, who could see with his telescope various objects like Jupiter and so forth, but with the Short, who could measure very precisely astronomical and collect astronomical data. Remember that year, it's the 1734. And as I said, the Kepler laws were due to the Tycho de Brahe. Tycho de Brahe was the last European great astronomer who didn't use a telescope. All the observations by Tycho de Brahe were made by the naked eye. And most of his experiments were done in this place, which you can visit. It is the island in the harbor of Copenhagen. And that is the original observatory of Tycho de Brahe, which Tycho de Brahe got from the king. The king, Danish king, had given him this observatory. And we know how much he paid for it, the king, how much the king paid for this observatory. And there is a number in some units, of course, but that would be too complicated. But I remember that amount of money because it was the same percentage of a king's purse, of a king's income, that the US government spent for the Apollo mission to land on the moon. This was exactly the same percentage of the one government purse and the other government purse. The Tycho de Brahe, the king died, and the next king wasn't really keen of sponsoring research anymore. So Tycho de Brahe left and became astrologist of an emperor of Germany in Prague, and that was not a very good idea because he died very quickly after moving to Prague. He was a strange character. He got involved in a brawl in a pub in Prague and lost his nose. Somebody cut his nose. So Tycho de Brahe produced himself a platinum nose, which he glued to his face with some kind of a glue. And the stories are that if he was in a quarrel and wanted to frighten somebody, he removed that nose, and he died on one of the parties of the king. He drank too much. And he left all his stuff for Kepler, who was his replacement. But that was in the Tycho de Brahe, and that's what I would like to show you are my own pictures, which I have taken in Jaipur, in India. And this is Jantra Mantra Observatory. This is the giant non-telescope astronomical observatory built in 1738, exactly at the same time when Short was making his enormous discoveries with the telescope. And this is enormous observatory with what is left from the biggest in the world astrolabium, which has been made by one of the very rich Indian. At that time, it were Moguls. There were still Moguls. So that was the story, and that is, of course, the other picture. And then you can see how huge are those devices. What was remarkable at the observatory was actually used for observations for 20 or 30 years, because at that time it turned out that this is even for those rich local moguls, it turned out to be completely ridiculous. But that is something really extraordinary. I must say, when I went to Jaipur, I didn't know about it. I knew about the Palace of Winds, and actually you go to Jaipur because you can take a ride on elephants to the castle, which is up there. And then all of a sudden I see the sign observatories. I went and I was completely flabbergasted. This is something. So so that was one part of the human activities which was a driving force for developing of the optics. And the other was the other extreme, to look at the small things. And that is, of course, the modern largest telescope in the world. This is the telescope, Gran Telescopio at Canary Island and on Tenerife. It's up there on the Teide volcano. So it's a huge microscope. The lens is 10 meters. The short was a 40 centimeters, and that's a 10 meter. But the other driving force for optics was to look at the small things, to magnify things, so we can see the little things. And this started with the gentleman Silvio Amato, who in the 13th century built, at least we are told that there were the first single lens glasses. And I don't know whether you might have seen this on the old pictures and the movies. There's something which is called pince. This is the glasses which are held there's a little bar attached to it. They not hang on your nose, you just hold it. And the Amato built something like this. And soon after that, there were just normal glasses. And then the people started to build something which we now call the microscope. And the first microscope built by the Dutch, and that the Dutch were the first, was by a fellow named Janssen, who made the first microscope. The magnification was 3 to 9 times. And then it was a Robert Hooke. Robert Hooke made himself a microscope, which was a single lens, and he wrote a book which is called the Micrographia. And then there is a person whom the high school textbook attribute building a first microscope. It was a Dutch craftsman, Mr. Leeuwenhoek, but that was not truly a microscope. It was actually a cleverly used magnifying glass. It was so in order to save his fame as a creator of a microscope, this device is called single lens microscope. And then we have a modern time microscopes, of course, today. These were the early glasses. You might remember the copy of them was used in the movie The Name of the Rose. And this is the microscope of Hooke. This is a single lens this is a picture of original microscope by Leeuwenhoek. The magnifying glass is, there's a little hole through which you look at the magnifying glass, and there were 2 screws, one which was moving the lens so you can get the better focus, and the other which moved that vertical bar which had a needle on top of it, so the displacement to absorb, which you wanted to see, could be put on that tip and move up and down so you can scan a certain region. And that is basically how the modern microscope look like. Today, I mean, the microscope, the part of microscope which is called ocular, those through which you are looking, I think, is gone. They no longer made the telescope like the microscope, because it's much easier to put a CCD camera there and then to show everything on a screen, on a computer screen. And you can buy a very cheap few dollars worth microscope, which has a fantastic also resolution. Okay, so that was a short history, and we start our lecture on optics from the basic law, and we start with discussing again electromagnetic waves at TEM, as we remember it. And that is the plane wave with the given equation, where the wave vector k is perpendicular to the amplitude E0. And as you might remember from a previous calculation, the magnetic field is then the perpendicular to the electric field and perpendicular to the k vector. So if you look at the propagating wave, you can envisage it as a line in three-dimensional space with a triad of vectors attached to it. The tangent to this line vector is a k, and the vectors E and H are perpendicular to it. And if you remember something from an analytic geometry course at the beginning of your education, you might remember that this is easily to describe by what is called the Frenet-Segre relations. There are mathematical equations which tells. So there are mathematical books which describe the optics using these geometrical things. I will not do this. This is the formula which you have to remember, at least for the lecture today. And the wave vector, the value, the length of that wave vector is inversely proportional to what we call the wavelength of the radiation, and this is just the square root of the inverse square root of the dielectric constant times the magnetic permeability. And as you remember, these two quantities are products of the epsilon 0 and mu 0, these properties of the vacuum, times a proper coefficients which we have. Okay. And if the electromagnetic wave is propagating not in the vacuum, but in the medium, then the very useful concept to describe it is what is called the index of refraction. And the wave of the speed of electromagnetic wave in the medium is, of course, depending on the value of dielectric and magnetic properties of that medium. So the ratio of the speed of the propagation of the waves in the medium to the velocity of light in a vacuum. Remember that we used the convention that the speed of a light in a vacuum is always denoted by a letter c. So the index of refraction n is this ratio, and that is given by the very simple formula. All right. So there's this extremely important and in some sense dramatic conclusion which you can draw from this trivial equation. Namely that if you calculate the ratio of the wave vector length to the index of refraction, then all of a sudden, this is a very simple calculation, this ratio is a ratio of a frequency over velocity of light. So it does not depend on the property of a medium. The property of a medium has disappeared. So this ratio is invariant. And that is what happens when the light goes via the medium. This formula holds, of course, for the medium which is isotropic. It will be modified if we have a medium which has different properties in a moment. But if it's isotropic medium, then it means that the wave frequency does not change. What changes is the wavelength. So if the light propagates through the medium, its frequency stay constant, but the wavelength get adjusted, and the ratio k over n is constant. And I will use it very often, at least today. Okay? So out of that comes this formula that the wavelength of the radiation is wavelength of in a vacuum divided by the index of refraction. All right. So if I shine on there's immediately a conclusion on it. If I shine on the medium, electromagnetic radiation, which is not monochromatic, which does not have a single wavelength, like the light emitted by a bulb, or this kind of a crazy lamp we have here in the room, then it is not it's not monochromatic. There are various wavelengths of radiation which are emitted. That they come to my medium, then all of a sudden each of the wavelengths of the emitted radiation will change. So that explains why the white light, which is a mixture of all possible wavelengths, comes out from the medium in a different way. So now the high school problem of reflection and refraction, and since the lecture is called Electromagnetism in Action, we will derive it from the Maxwell equation and the boundary condition. So this is basically the picture we have. We have two mediums, 1 and 2. Each of them has the refraction index, which are basically different. And since this is a boundary of two media, I will conveniently denote this refraction index by N1 and N2. And there is a wavelength which comes in, and it's incident beam. And this red line, which you remember from the high school, is this line to which the vector k of the electromagnetic wave is parallel. Okay? So what happens to the magnetic field in the coming wave? It is perpendicular to that line, so there may be various directions, right? We may have a various possibility. And let's focus our attention on the electric field. So the electric field of that wave might be in any direction perpendicular to that red line. But since this is a three-dimensional space, and I already have fixed the one direction, then the electric field is in a plane which is perpendicular to this red line. So it's a two-dimensional plane, so the base in it, geometrical base, are two vectors, and therefore I can, any electromagnetic wave coming to my interface, describe using just two vectors. The one vector which is perpendicular to the picture plane, and the other which is in that plane. And out of these two vectors, I can combine any electric field I want. And of course, similarly, I can do with the magnetic field, because the magnetic field is also perpendicular. The only difference is that if the electric field is pointing out of that plane, that the magnetic field must be in the plane, because they are perpendicular. But that is basically the same. So this light comes and it scatters. The important part in my mathematics is played by the vector which is perpendicular to the interface, the normal vector. And for sake of convenience, this is a vector. So the vector, I will be using a vector which points out of the interface. It points out of this grayish surface medium into the white medium. And therefore what happens is that the light reflects itself and bends itself. And you know it exactly from everyday life. So now let's recall the boundary conditions for electromagnetic fields. And I consider this medium to be dielectric. There is no surface current, there is no surface charge. So my boundary conditions are pretty simple, and they read as on these equations, and I can write them using either a displacement field and the magnetic induction, or electric field and the magnetic field. And in each case, the continuity of a normal component and continuity of a tangential component are written in this form. So I have two equations. One where these fields are, the difference of the fields is perpendicular to the vector n, and the other which are the vector product is equal to 0. So these are my boundary conditions. And then if my electric field is the TEM wave, that which we are discussing, then the equation for a continuity of a tangential component for the electric field is explicitly written below. It's a lengthy equation, but out of that equation we can derive many fundamental conclusions. First is that this is a boundary condition and the field is time dependent. And that condition must hold for each moment of time. Therefore, this formula holds for any t. And that is only possible when all the frequencies are equal. Otherwise, I will not be able to satisfy that equation. So I have one conclusion, that the frequency of incoming, I mean, that should be different formula, but I mean the frequency of incoming wave and reflecting wave and transmitting wave must be equal. That follows also from the fact that the k over n is constant. Okay? So now we have that equation must also hold for every point on interface. I mean, this vector, I draw the picture, but its translation invariant. I mean, if I shine the light on that table, it's the same thing must happen here as here. So that means that this equation, this difference of the electric fields with the phases and so forth, that must hold for every point x, and therefore the conclusion is that the k1 times x times k1, I use the notation that the prime denotes the reflected wave, and the index 1, at least in this slide, means the wave which is in medium 1, prime means this is a scattered wave, and the index 2 refers to the wave in the other medium. So this is a scalar product, so it's very simple formula which I have here, and therefore I immediately get a relation that the wave vectors must be the same, so the wavelengths are the same, and therefore the product must be the same, and out of that follows that the angle θ1 is equal to the θ1 prime, and that is what we know, that the angle of incoming, this is one of the Snellius laws, that the angle of reflection and incoming angle and is equal to the reflecting angle. And then I can use the formula that the ratio of a wavelength, of a wave vector k over the refraction index must be constant. So if I use it, and I again use my equation for the products, vector product, then of course I have the relation that the ratio of the refraction index is equal to the ratio of the sines of the angles. The important thing is that there's a difference that it's n1 over n2 is a sine of θ2 over θ1. And this is the Snellius law, which we all know. So that is as much as we learn about the tangential component. I'm sorry, I have to go back. How do I go back? Okay, and that is what I can use to describe the phenomenon which you know from everyday life. Namely, if you put the spoon into a tea, it looks like it is bent. Okay? That is explained by this picture. I have the wave, electromagnetic wave, which comes to a slab. It reflects and goes into the medium. Then it comes out of the medium. And therefore, these incoming and outgoing beams are parallel, but they are shifted. So that is something which we can use in the optical devices in a very convenient way for various applications. But that was all when the medium was homogeneous. But I would like to spend some time discussing the phenomenon which is called birefringence. Birefringence is a phenomenon which you can easily observe. That is a picture of a plastic spoons which you can buy in a supermarket, and you shine a line on it. And it's also the picture which, or you may not have seen it, but I mean, if you drive the car, modern car, and the sun is shining straight into your windshield, and you are using a cheap sunglasses, not very good sunglasses, all over the sudden the windshield will turns out into the color patches. That is precisely the same phenomenon. Why? Because a windshield in a modern car is not a piece of light, of glass. It's a multi-layer structure, multi-layers, very thin layers of a glass, and in between them there is a certain transparent sort of a glue which makes this glass safe. And that is why when you hit something, the windshield does not split into the big pieces which can cut your head off, but breaks into little diamonds, which then are everywhere on the street. And that is why you also see the birefringence, these color patches in the car. But you need special glasses, and we will come to that in a moment. So this is a picture all over the sudden. The medium has the index of refraction, which is depending on the polarization. So what is the polarization of a wave, of our electromagnetic light? As you remember, we wrote the TEM wave as a certain amplitude times a function of time and space. And that amplitude is a vector. So that vector, the direction of that vector, is called polarization. And in this experiment we were discussing, when there is a light coming and where the wave vector k is along the ray which hits the interface, then these two directions of electric field I was discussing, one which is perpendicular to the surface and the other which is in, they are two different linear polarization. But of course, in general, the wave consists of both polarization. So if they are both equal, then this is called the circular polarization of the light. And there are media crystals which we used to say they have an optical axis. And it turns out that the index of refraction depends on the angle on which the wave electric field or magnetic field makes with that angle. And if the index of refraction depends on that angle, then of course different polarization are scattered and deflected in a different way. And there are lots of materials with that example, those plastic spoons and knives. That was one of the examples. But there are more interesting examples, like a quartz, a crystal quartz, a calcite and a sapphire. And there are artificially made optical materials like a lithium niobium trioxide, which also exhibit those birefringence situation. So what happens when you have a birefringent material? There is a light which comes, and it's a light where I draw the two polarization. The one polarization is in the plane of the drawing, and the circle denotes this other polarization, the electric field, which is perpendicular to the plane of the picture. And they hit the crystal, and if they hit the crystal, then these electric field vectors, the polarization vector, is at angle on which with respect to the optical axis. Therefore, the index of refraction for one polarization will be different than the other. And if the crystal is cut in such a way that the axes are properly chosen, then the one polarization wave goes through and the other scatters at different angle. And the opticians called one of those beams normal and the other extraordinary. And that is, of course, if I have such a material, then I can play all sorts of various tricks with that material. And this is a full picture of the vectors and on the arbitrary way, but we will not do it. And this is, I just wanted to show you the one device, which is called the quarter of the wavelength plate. It's the wave which is cut such that if the linear polarized wave comes in, it comes out circularly polarized. If it comes circularly polarized, it comes out linearly polarized. That explains the word quarter wavelength, because the phase is turned by 90 degrees, which corresponds to the half of the wavelength. There is a nice story about this quarter of the wavelength plates related to the physics department of the University of Warsaw. There was an optics laboratory there, and in each optics laboratory there is a quarter of the wavelength plate. And years ago, there was a kind of a controller who came to the lab at the University of Warsaw and was checking whether everything is there, where nothing was stolen or lost or something. And he opened up a little big book where there were various items in the possession of the optics laboratory were written, and looked at it and put his finger on and said, okay, I would like to see your quarter of a wavelength plate, number, whatever. And my friend, who was assigned a job of taking care about this controller, went to the shelf in the lab, picked up a little nice box in which that piece of glass was held, and gave to him. And then this controller exploded, saying, you think that I am so stupid, you want to cheat me, I will put you in, well, anyway, and ran out of an office and ran out to the director of the institute. And soon enough, my friend was summoned to the director of the institute to explain what happened, why they were cheating the controller. And they said that they have shown him a quarter of a wavelength. They have no foggiest idea why this guy had. And what turns out that this controller a few months before, was doing a similar control in the physics department of Warsaw Technical University. And for some reasons, he asked the same thing. He wanted to see the quarter of a wavelength plate, and they couldn't find it in the laboratory. And they thought that this is a dumb controller. So you might have seen this ruler which technicians use, which you can fold into 4 pieces, right? The wooden meter measuring rod, which consists of 4 pieces, so they can bend. And there are 4 pieces, so a quarter of the wavelength. And they have produced this thing. And well, he accepted it, that this is called a quarter of a wave. And now he saw a piece of glass. So they are obviously cheating. So that is a story with the quarter of a wavelength. All right. So now we have a time to derive fundamental equations. Finally, something which is not as simple as a Snell law, and that is, these are the so-called Fresnel equation. And so far, I use only the property of a phase of the wavelength, right? The fact that it was the phases. And now I will try to calculate the relations between the amplitudes. And the Fresnel equations relate to the amplitudes. And again, we have our boundary conditions. And and now I have, well, I apologize. Soon I will become consistent. Now 0 is the incoming wave, and 1 is the scattered wave, and 2 is, I get tired of these primes, right? So, and now we will try to use these relations. And I also had written the magnetic field for each of these components. And there's a simple algebra which tells me that actually a magnetic field is the vector product of a wave vector and the electric field. And there is this coefficient which is well, if I want to simplify my life, I will work in the units where epsilon times mu is equal to 1, but I try to avoid it. Okay? So now I will substitute this equation for magnetic field into my boundary conditions, and then the boundary conditions will be accepting a shape which is called star, and that is the formula. As you see now, I have a complicated situation because I have a triple vector product. But this is our formula, which is we always use. The triple vector product is one of the most useful formulas in mathematics. A times B times C is this, A, B, C is BAC, BAC minus CAB. Remember, you have to remember this formula, and therefore I will use this now, and that is again the picture which I'm using. It's my previous picture, but now because I copied that picture from some book, I have to adjust my algebra to that particular picture. So from now on, an incoming beam will be denoted by I, incoming, reflected beam by a letter R, reflected, and the transmitted beam by a T, transmitted. So I have the incoming beam, and I have the electric field which is perpendicular to my plane. And I will study 2 cases. This case number 1, where the vector electric field is perpendicular to the plane of the picture, and the other where the electric field is in the plane of the picture. So I have these 2 cases, and I will first discuss the case 1 and then the case 2. And if I have the case 1, then out of this complicated vector product equation, I get a simple scalar equation, that the amplitude of incoming radiation plus the amplitude of the reflected is equal to the amplitude of a transmitted wave. So then it is relatively easy to write my formula in that way. And that reduces to the simple scalar equation of that form. And as you see, there are amplitudes, and I have this relation for amplitudes, that EI plus ER is equal to IT, and I have these cosines, right? And I have my relation, which I already derived about the sines and index of n. So now I can, this is a course of trigonometry, which I will skip. Every calculation now is a high school calculation in trigonometry. You have two angles and you have the equal amplitudes. So there is a messy, simple high school algebra. Actually, I try this derivation of my grandson, who is now taking a trigonometry, to force him to learn how the sine of how the products of sines related to the sine of a sum of angles and so forth. You remember there are lots of these identities, trigonometric identities, which you have to remember. The easiest way is to turn every sine into the tangent. But that is just a trick. You have to remember, believe me, that I have solved that algebra correctly. And out of these two equations, I can arrive the relation between the reflected amplitude and the scattered amplitude when the wave vector E is perpendicular to the plane of in which the radiation falls on my interface. So this is one of these formulas. We will remember it. And this is a Fresnel equation number 1. This relates not to the angles, but to the amplitudes. Now I will be looking at when the electric field is in the plane of and then I will use again this equations of continuity, but if it's in the plane, then everything simplifies, and instead of this, or not simplifies, but makes more messy, depends on what you want. And first, when the vector electric was perpendicular to the plane, then it was EI plus ER is equal to ET. Now it is EI times the cosine. So it's again a trigonometric expression. And then is a vector equation. And again, when I use the triple product, then I derive this equation. So you see, in some sense, these equations are very similar, but depending whether I'm in a plane, whether my vector is perpendicular to the plane or in the plane, then somehow these trigonometric coefficients change. Okay? And again, I use the trigonometry, and I derive this equation. And this is the Fresnel equation number 2. So now I have two sets of equations, which I had written in one form, and that is so let's look at now on the equation number 2, which are for some sense more interesting. And then let's look at the reflected amplitude. This is the wave, the electric field is in the plane of the picture, and we look at the amplitude of reflected beam. So we can clearly see that the reflected beam amplitude might vanish. There will be no reflection. And one solution is where the angle T, the reflected angle, is equal to the incoming angle, the transmitted angle. So that means, but when this can happen? if the incoming angle is equal to the transmitted angle, then there is no difference in the material. So this solution is somehow trivial. But there is another solution for ER equal to 0. This is when this tangent of a sum of the angles which sits in the denominator diverges. And when it diverges, is infinite, then ER is also equal to 0. And it diverges where the sum of those angles is equal pi12. And then the situation is very interesting. Namely, if it's that equation, then we can plug it into the Snell law. And it turns out that the ratio of the coefficients, refraction coefficients, is equal to the tangent of that particular angle. So if the wavelength, if the incoming angle for the radiation which is in the plane of our picture, okay, is equal to this Brewster angle, then there is no reflected light. And that is how the, and that was the formula which was known for years and years. And that was used by a certain gentleman with the name Edwin Land. And I would like to finish with a few words about him. He was probably one of the last geniuses of the conventional optics, so to say. He went to the MIT as a student, and he was a freshman on the first year, and he was walking over the physics department telling all the professors that he knows how to create an arbitrary color, not using 3 colors, as the theory tells us, but using 2 colors. So eventually he was talking to the famous Professor Morse, very extremely brilliant scientist, who thought, Lang, why don't you take a book and learn that you need 3 colors to create arbitrary other colors? So stop talking this nonsense. And if you still believe it, then you better leave the MIT. So that's what Land did. He left MIT, and he set up his own company. And the first thing he did, he built up polarized sunglasses, a device which uses the Brewster angle. If there is a sunlight which scatters from the surface, it becomes linearly polarized. And when it falls on the glasses, which under the Brewster angle, then there is essentially no transmission, it's on, and therefore you don't see. You have much less intensity of a light coming to your eyes, and this is a picture of the sunglasses by Mr. Land, and this is from 1929, and soon you see the 36, and you see how the fashion changes, and the sunglasses for 36 are essential as we were today. But then the war came, and Mr. Land got involved in the war business, and he makes lots of money by producing very cheap optical devices from plastic. He learned how to make binoculars from plastic, and they were costing less than $1 a piece. They were very bad, not very accurate. But that provided the American army with possibility of giving binoculars to every soldier. The German army had the fantastic Zeiss devices which cost a fortune. They were nice and superb with enormously high quality, but they were expensive, and the Americans were very cheap, but nobody counted them and so forth. As you know, also they make the watches for the soldiers. The name of the watches was Atlantic. And after the war, there are these movies showing the American soldiers leaving the army, going back to the United States, turning the glasses when they were boarding the ship, and the German prisoners of war with the big hammers destroying those watches. Europe was flooded with those watches. Of course, they were, part of them were not destroyed and so on. So Edwin Land built up mega money, and after the war got involved in a business which was making an instantaneous photography. This is one of these apparatus. And he was making color pictures cheap because they were generating the color pictures from two paints. And that it is quite possible to mimic extremely well, essentially every color by tricks used by the Mr. Land from two colors. And then he left his company and come back to MIT as a kind of associate professor, and without having any degree, and donating lots of money to the institution and so forth. And eventually, he invented an instant film camera. It was, but that didn't catch, because at that time we moved from the normal pictures into the electronic pictures. And that, of course, also is an interesting story, because there were two brothers, Hunt, who had stolen a silver, and there was no silver to make films. So people were thinking that since the silver is so expensive and this procedure of developing film is so messy, so why don't we invent something which will replace it? And well, now nobody does anything else than doing electronic pictures, and the company Polaroid has disappeared. It exists as a trace company which sells these devices for fans, but that's a minor operation. So that was about the Fresnel formula, and we will continue next week. Thank you.